So I'm going to talk today about a new topic called sparsification, but it uses some of the ideas from yesterday and it also uses some of the ideas from before, right? It doesn't have any designs in it, but it uses some spectral graph theory and it uses spectrahedra and things like that we saw yesterday. Okay. So this is a talk that I've given before, that's why it looks like this. It's joint work with my collaborator, Stefan Steinerberger, who's also my collaborator for everything else I told you. And then my student, Catherine, who is now at Caltech. Okay. So this was a general talk, so you might see some things again that you already saw. So hopefully it's a refresher and not too boring. Okay, so what are we trying to do, right? So I have some graph, G. It has n vertices and the edge set is E. And for today, we'll assume there are weights. Okay, so there are weights on these edges and they are positive weights. Okay, so no zero weights on the edges, but positive weights. And the idea of sparsification is you want to throw away some edges from this graph. So you want to keep the vertex at the same, n, but you want to change E to E tilde, where E tilde is a subset of E. So we want to throw away edges, and you're allowed to put new weights on the edges that remain. Okay, so you're allowed to reweight the edges that remain, but the idea is to decrease the number of edges in the original graph. Okay, this is called a sparsification, right? So we have a graph where it's very dense maybe. We would like to throw away a bunch of edges and to get like a subgraph. Okay, so this is without any further qualification, this is what it means to sparsify the graph, right? And this may have different uses because it could be the graph is used for something, but it's too much information, so you just want to retain the important edges and forget about all the other edges. But it's not really clear how to sparsify, which edges to throw out, which edges to keep, how to reweight. None of this is clear, right? But just without anything, this is what it means to sparsify. Everybody okay? Okay. So for example, this graph that has all the edges that you see here, the blue and the black edges, this is called the lollipop graph inside Mathematica. And we'd like to sparsify it. And the key property we want to maintain is that we want the sparsifier to preserve the important properties of G, right? We don't want to just throw away edges. We want the sparsifier to be a proxy for G, right? It should behave like G. Otherwise, there's no point, right? Otherwise, we get something completely different and we're not really getting any benefit from throwing away the edges. We're getting actually wrong information, right? So this is kind of the meta philosophy. We want the sparsifier to preserve properties of G, at least approximately, okay? So for example, if G was connected, I would like the sparsifier to also be connected. That's a very basic thing. But maybe we want to preserve more properties, okay? All right, so we'll see this lollipop graph again later. And you'll see what these blue edges mean. But in this graph, for example, if I remove all the blue edges, the graph is still connected, right? And it essentially preserves the structure of the lollipop, right? It has the long tail, which you can't mess with, because if you remove any of those edges from the long tail, you'll disconnect the graph and it's a completely different object. So it seems like you should not mess with the tail. But in that complete graph that you see on the other side, maybe we could throw away everything as long as it stays connected. It seems like a reasonably okay way to sparsify. And later we'll see that it has an actual meaning, okay? So you can throw away these blue edges and still preserve certain things. Good? Okay, this is what sparsification is. This is a very big deal. So it's a very big topic in computer science. They like to sparsify graphs, partly because the motivation comes from the fact that there are linear systems you solve that have the structure of a graph, okay? So there's a matrix, n by n matrix, and it looks like the adjacency matrix of the graph, except that in the positions of ones, you put like whatever numbers, okay? There are other kinds of numbers. Or it looks like the Laplacian of a graph, and instead of putting the actual Laplacian numbers, you put whatever numbers. So the underlying structure of the matrix is like the Laplacian of the graph on which the matrix is supported. Or does that make sense what I'm trying to say? So if you have a matrix, it's symmetric, and you can look at where are the non-zero entries, and that'll build for you a graph where in the non-zero entries you put an edge, okay? So there's a graph structure that sits behind matrices that look like Laplacians or adjacency matrices. So these kinds of, so if you have a matrix like that and you want to solve, say call it A, you want to solve AX equal B, okay? You want to solve this for very, very large size thing. Then it might be that if you sparsify the graph, you just throw away some of these entries from the matrix and then solve AX equal B. And if the solution is close to the original, it's very good, right? You don't have to solve a big dense system, you solve the sparse system. So this is where the motivation comes from. And these kinds of systems routinely appear in, for example, interior point methods in optimization. There are large systems that look like Laplacians. And you need to solve them over and over again. So if I know that I have a sparser system I can solve, it's better, okay?
So when you say look like Laplacians, I understand that the non-zero entries
are
in certain positions.
Yeah.
Why is it not a Laplacian?
Because it's only like weakly diagonally dominant oftentimes, right? So Laplacians are diagonally dominant in the sense that, or weakly, because we know that the Lii is equal to minus the sum of Lij for all j that's in the same row of I as I, right? So in the matrix, the diagonal is the biggest entry. And then if you sum all these guys, it's going to be smaller or equal to this one, okay? So the Laplacian is an example of a diagonally dominant matrix. And these, it's actually weakly because it's actually equal. But in interior point methods, you often have weakly diagonally dominant systems that you need to solve. So you look at the graph structure behind it, and then you say, okay, let me throw away a bunch of edges in the graph, get a new system, and hope that the solution is close to the original solution, okay? So you cannot just throw away whatever edges. You have to be careful. But there are these big results in computer science that show that you can always sparsify a graph, and it'll give you, you can always sparsify graphs and guarantee that you will only be left with some amount of edges that depends on the degree of the original thing and n. Okay, so this is the idea. So let's talk about so I'm going to introduce to you a model for sparsification. That's the goal of this lecture. And then we'll look at the space of all sparsifiers under this model, okay? Okay, so we have the graph Laplacian that you have seen already yesterday. So it's a positive semi-definite matrix L, and it's defined like this, right? Like in the ST entry, you put minus the weight that sits on the ST edge, if ST is an edge. And if ST is not an edge, you put 0. And in the diagonal entry, you sum up everything in that row, negate it, and put it in the diagonal. Okay, so this is the Laplacian from yesterday. And I think this is just a small example. So in this example, we have a triangle that's weighted like this. This is the Laplacian. Can everybody just verify quickly? This is the Laplacian. And this Laplacian is PSD. So in this example, we expect 3 eigenvalues. And indeed, there are 3 eigenvalues, lambda 1 equal to 0, with the all ones normalized as the eigenvector. Lambda 2 is 4, this is the eigenvector. Lambda 3 is 6, this is the eigenvector, okay? So this is what we expect in this tiny example. And in general, we have what you see up there, right? So the eigenvalues start at 0 and then go up. And the first eigenvector is always all ones divided by root n, if I normalize. And the rest are orthonormal and so on, and they go on, okay? So we've seen all this already. So this is the graph Laplacian. So I'm going to use this Laplacian to do my sparsification. Okay, so what are we doing? Oh, before that, let me tell you these famous results. So there is a result, there is a model of sparsification due to Dan Spielman, who's at Yale, and Tang, I forget his first name. So it's called the Spielman-Tang sparsifiers. And what they do is the following. They look at the quadratic form of the Laplacian. Okay, so Q of x is x transpose Lx. Remember, we saw this was a convex function. So they look at that. And then remember that if there were no weights, it was sum of xi minus xj square, right? If there were no weights, we worked it out, right, with the BB transpose. If there are weights, the adjustment is you have to put the weight next to the xi minus xj square. Okay, so that's the expression for the quadratic form. Good? Okay, so they are going to call, their model is like this. Okay, they'll say that G tilde is a spectral sparsifier of G if the quadratic form of G tilde is sandwiched between the quadratic form of G on both sides with two constants alpha and beta. Okay, so if I take the quadratic form of G tilde, let's assume it's red, I want it to be at most beta times the quadratic form of G and at least alpha times the quadratic form of G. Okay, so the quadratic form of G is what the scaled versions are what I'm putting in the dotted parabolas. Okay, so let's assume that the red one is the quadratic form of G tilde. It's a convex function, so it looks like this. And then I want this to be sandwiched between alpha times the quadratic form of the original graph and beta times the quadratic form of the original graph. This is, you want to squeeze the alpha beta as small as possible. Okay, so in general this is possible. I'll show you their result, but this is their general definition of spectral sparsifier. Okay, so they are just trying to approximate the quadratic form, right? They want G tilde to have roughly the same quadratic form as the original G. That is their notion. And what they prove is the following. This actually joint with Nikhil Srivastava. They proved in 2012, this is a very famous result now. It says that if for every d bigger than 1, so d is not the degree, it's just a parameter. For every d bigger than 1, and for all graphs G, there exists a sparsifier, G tilde, with number of edges at most this much. Okay, you give me the D and you give me the graph, then there will exist a G tilde, which is a sparsifier, which has at most this many edges. Okay, so D is given to us, n minus 1, n is the number of vertices. So you're guaranteed at most this many edges such that the alpha and the beta look like this. So the quadratic form of G tilde is bounded above by this times QGX and that times QGX. This is what they proved. Okay. So what happens if as D increases? So if as D increases, what will happen? This number will increase, right? So 1 over that number will decrease and you'll get closer to 1. Okay? So as D increases, this number will decrease. It'll get closer to 1, and similarly this number will decrease and it'll also get closer to 1. Okay? So if you allow bigger D, you can squeeze much more. Okay? So if you allow a very small d, okay, you won't get it to be too much close to each other. But as you allow bigger and bigger d, you will be allowed, you'll get a better and better approximation to the original quadratic form. But then the number of edges will also go up along with the d. Okay? So it's a trade-off. You decide how much you want to squeeze, and then depending on that, you'll be guaranteed that you'll only have so many edges. Okay?
And this is saying that you only have linearly many edges.
Exactly. You only have linearly many edges as long as d is not some function of n in some bad way. Okay? So it's a very nice result. It's a very nice sort of general guarantee. The proof of this is very complicated. Okay? It requires the usual use of polynomials. What are these, like real stable polynomials? It's a fantastic result. But I forget. They have a series of papers, and they use pretty deep results in mathematics to actually prove this. So it's not just a one lecture proof type of thing. although you could at least see the highlights in the lecture, okay? So they have a bunch of different results. This is one of them. And this is what they guarantee, okay? So at the end of the talk, I will come back to the Spielman-Tang model and compare it with our model. I'm going to give you a different model for sparsification, okay? Okay, so what did we learn on day one, right? We saw spectral graph theory on day one. We learned that the low frequency eigenpairs of the Laplacian control the structure, the global structure of the graph. For example, G is connected if and only if lambda 2 is positive. G has K clusters if and only if the first K eigenvalues are 0. So it's the low ones that are actually controlling like global structure, right? The connectivity, the number of clusters. We saw that the mixing time of random walks are controlled by lambda 2. This was the folklore result, right? Mixing time means the amount of time it takes to converge to stationary distribution. So we saw that that convergence rate is controlled by lambda 2. We saw that the sparsest cut is bounded by lambda 2. Remember this from day one. We saw that the second eigenvector produces a pretty good sparse cut. We saw that if you take two eigenvectors, you get, yesterday I told you about spectral embeddings. So if you take the first two eigenvectors, you get spectral drawings. So here are some pictures of spectral drawings that we didn't see yesterday, okay? So for example, in that graph, that's the dodecahedron graph, the top, the graph of the dodecahedron. If I take the second, third, and fourth eigenvectors of the Laplacian and use them to embed the graph. So remember what that means? So phi2 and phi3 and phi4 are two long vectors. And then we're using the rows of this n by 3 matrix to position the vertices of the graph, okay? And then we are connecting things together if there are edges. So if you use those three, you see the graph looks like the graph of the dodecahedron. It's not just like some graph you put on the plane with some dots and then you connect, right? Because a graph is an abstract thing. I could just put 10 dots. How many vertices does this have? Is it 10? 1, 2, 3, 4, 5. I don't know. How many ever? Dodecahedron. 15, okay. So you could put 15 dots in the plane and just connect whatever you need to connect. But if you use the eigenvectors, you actually get an embedding that looks geometrically like the graph of the dodecahedron, okay? So these spectral embeddings are quite nice.
So drawings is the same as embeddings here?
Yeah, spectral drawings, by that I mean spectral embedding, the same thing we saw yesterday, okay? But then for the same dodecahedral graph, if I use the last, wait, how many does this have? 1, 2, 3, 4, 5. No, it has to have 20, if my calculation is right. It's 20, right? Yeah, okay. Please check, it has 20. Yeah, okay. It has 20, okay? So I could embed this graph using 3 eigenvectors, or 2, or any number really. So if I put it in 3, I can see it. That's why I use 3. So those are the low eigenvectors. Here are the highest 3 eigenvectors. If you use that, this is what you get to embed the graph, okay? So if you use high, eigenvectors with large eigenvalue, you get like messy stuff because it is very, oscillatory. Whereas if you use the low eigenvectors, you see something nice, okay? So the key thing, so these pictures are from Spielman's book actually. So the key thing that I want to emphasize is that the low frequency eigenpairs, the eigenvalues and eigenvectors that are low compared to the low, for the low eigenvalues, they are actually really important for the graph, okay? So what we want to do now is we want to create sparsifiers that preserve this low part of the spectrum. I want to keep the low part of the spectrum intact, and then I don't care what happens after that. That is going to be my model of sparsification, okay? So that's going to preserve all these kinds of properties, but you will still lose edges and so on, and it may not preserve some of those high stuff which doesn't really control the global structure of the graph. So it makes some sense, right? That this is a reasonable model of sparsification. It's not the quadratic form. It's really, we're going to freeze the low part of the spectrum, Okay, that's the idea. I don't think the pictures are from there, but you can see lots of things like this in Spielman's book, or maybe they are from there, I forget now. Okay, so here is our spectral sparsification heuristic. So I'm going to call G tilde K isospectral to G if lambda I of G and lambda I of G tilde are the same for I from 1 to K. Okay, so I want the first K eigenvalues of G and G tilde to be exactly the same, but I want more. I also want the first K eigenvectors of G and G tilde to be the same. Okay, so it's very strong. So because I want my Fiedler vector and all that, I want to keep it intact. Okay, so I'm going to freeze the low part of the spectrum, the first K eigenvalues and their eigenvectors, and then the rest we don't care. Okay, so G tilde is called K isospectral to G if the first K piece of the spectrum is common to both G and G tilde. Everybody okay? Okay, so yeah, so K, what am I saying? Okay, so that's what it means to be K isospectral. Correct, so pick some. I mean, we are allowed to have multiples are okay, but if you have a fat eigenvector space, you have a different choices of eigenvectors, right? So let's fix an orthonormal basis for G and then freeze the first K. Okay, so there I do have some choices. The multiples are less problematic than if you just chose a different eigenbasis for an eigenspace, you could have. But I'm just saying pick one, freeze the first K. Okay? Okay, so that's what it means to be K isospectral, and then we'll call G tilde K sparsifier of G if G tilde is K isospectral and the edge set of G tilde, which is E tilde, is inside the edge set of E. Okay? So we want the edges of G tilde to be a subset of the edges of G. Okay? So in this definition, it doesn't mean you will lose anything. You may not lose anything. Maybe all the E tildes are still there. I mean, all the edges are still there. But in the good cases, we will lose. And E tilde will be a proper subset of E. Good? We're allowed to change weights. Okay? So we're not trying to, this is not an unweighted situation. Oftentimes, the weights will change for all this to work out. Okay? So some weights might become very big actually to rebalance things. So weights are fine. We're not too concerned. Okay. So now here's the lollipop back again. So what the original graph is blue and black. And if you remove all the blue edges, then what you get is a 3 sparsifier of the lollipop graph. So that means it's this black graph preserves the first, the second, and the third eigenvalues from the original and the eigenvectors, the phi1, phi2, phi3 from the original. Okay? So this graph has 12 vertices and 26 edges, and we've dropped a lot of edges, right? There's so many blue edges there that got dropped. So you end up with just the black edges, and that'll freeze the first, that's already able to freeze the first 3 eigenvectors and eigenvalues. Is this okay? So this was not an arbitrary picture. So in particular, it preserves connectivity because it's freezing lambda 2. It preserves cut structure because it's freezing lambda 2 and phi 2. And it's actually also freezing lambda 3 and phi 3. Okay? But we could have frozen up to 12, right? Or up to 11, we could have frozen the eigenvalues and eigenvectors. I'm just freezing the first few. That's all I'm trying to do. And then I run it, and you see, okay, I can drop all those blue edges, and that'll be fine. Okay? So this is my notion.
It looks like there should be a theorem that you should not be able to do it for K lambda.
Yes, so we'll see that. So there will be a bound below which it won't sparsify. Above which it won't sparsify. Correct. Okay, so before we do anything, let's look at some examples so you see what this actually looks like. Okay? Let's take this thing called the butterfly graph. This is in Mathematica. It's called the butterfly graph. It's also in the notebook that you have right now. So this graph has 5 nodes, and these are the eigenvalues, 0, 1, 3, 3, and 5. Okay? So there's a multiplicity on the 3, but that's the eigenvalues. And let's suppose we choose k equal to 2. That means I want to freeze the first 2. Okay? K is what we are freezing, the number of things we are freezing.
And you're taking unweighted.
Yeah, in the beginning it's unweighted. So let's assume it's unweighted, but after you sparsify, it might get weights. Okay? All right, so lambda 1 is 0, and we know it's eigenvector. These 2 are for free. We always want to freeze this. Okay, we always want to freeze this because every Laplacian definitely has that property, right? Has to have 0 and all 1. So that's for free. And then I'm also going to freeze the second eigenvalue and its eigenvector, which is this. Okay? But I'm allowing 3 eigenvalues and 3 eigenvectors to change. So that is the freedom that we have in this picture. Okay, so in this picture, we will compute this in a bit. But let me show you the answer first. So what's going to happen is the 2 isospectral subgraphs, which are the ones that freeze the first 2 eigenvalues and eigenvectors, will look like this, okay? So what you will have to definitely keep these edges, okay? So the edges that emanate from 1, you have to keep. But this edge, the 3, 2 edge, you can change the weight on it. It's called A, and A is non-negative. So in the very worst case, A will become 0 and this edge will go away, okay? You can also play with the weights on this, and it's any B greater equal to 0. You can make both A and B 0, and so those are the possibilities, okay? Anything like this will be 2 isospectral. So the space of 2 isospectral subgraphs is basically controlled by A and B, right? So it looks like the positive orthant in R2. When A and B are both 0, you get this graph where you dropped both blue edges, okay? So the origin corresponds to this graph. This is 2 isospectral. This whole axis here means that B is 0. So they're all graphs that look like this, but you're allowed to change the weight of A all the way, okay? So as A increases in the x-axis or A-axis, you parameterize all the graphs that look like the bottom. Similarly, on the y-axis or b-axis, you get all the graphs that look like this. And in the middle, in the interior here, you get all the graphs that have all the edges, but A and B are whatever you want to pick it to be, right? Like if I pick A to be 2, B to be 3, I'll get a dot 2, 3, which will carry that particular graph.
Okay. Should not remove edges from 1.
That's how the calculation comes out. If I force to freeze the first and second eigenvalue and eigenvector, we'll see that the calculation forces you to keep the 3, 4 middle ones.
Maximum degree.
So, it's something, okay? It's, yeah, if you drop any of them, the eigenvalue and eigenvector that's either phi2 or phi1 will change, okay?
But it's a bit surprising that it does not change the weights on those.
It doesn't. Yeah, we'll calculate this explicitly and check that this is the answer, okay? So it's a little surprising. It's not a priori clear what's going to happen, but in this example, this is what happens, and we will see how to, so what I want to calculate is this parameter space, okay? So there is a space of sparsifiers, this yellow thing, okay? In this case, it's a polyhedral cone. Everybody okay? It's just the positive orthant in the AB space. So it's a polyhedral cone. So it looks convex, okay? It looks polyhedral. Okay, it's a cone. So you might, based on this example, you might think that all these regions are polyhedral. Maybe these regions are always convex. Maybe these regions are cones. Okay, all kinds of things. Okay, so let's do a slightly bigger example to see what will happen. Okay, and all the properties we just listed, you'll see will, some of them will stay, some of them will go. Okay, any questions on this? Is this okay?
Go back to, I couldn't go down 5. Yeah.
Okay. Okay, so that's the picture. This is the space of sparsifiers, the yellow stuff. Okay. And then you can also because I know the weights and so on, I can write down all possible Laplacians. It'll look like this. Okay, this is easy. For example, so remember the first node is connected to 2, 3, 4, 5. So it'll have these. The first row and column are fine. And then the second node is connected to 3 and 1. So in 3 and 1, you will get something, 3 and 1. So I didn't put the lower part. So in 3 and 1, you get something, and this is just the Laplacian, okay, with the weights symbolic as A and B. Okay, so that's a space of all Laplacians. I had 2 isospectral subgraphs and their Laplacians, and we'll denote it like this, okay? SPG2 means sparsifiers of the graph G, where we have frozen the first 2 pieces of the spectrum. Okay, so what's in the bracket is the K, the number of eigenvalues and eigenvectors we're freezing. Okay, so now let's do a more interesting example. Let's look at K4, the complete graph on 4 vertices, okay? So we already calculated this many times, right? That the spectrum, the eigenvalues are 0, n in general. So in this example, it's 0, 4, 4, 4. Yeah, that's the spectrum. And again, I'm going to choose k equal to 2, okay? But now I'm doing something slightly fishy, because I'm actually cutting the there are only 2 eigenspaces, the all one span and then the complement, right? Now the complement is just one fat eigenspace, and I'm going to choose one eigenvector to freeze. So I have a lot of freedom which one I choose to freeze, okay? And here you'll see that the answers will depend on which one you choose to freeze. If you choose an entire eigenspace to freeze, there's no problem. But if you cut through an eigenspace and freeze some part and don't freeze the rest, it depends on what you froze. The answer will depend on what you froze, okay? So I'm choosing this eigenvector to freeze. Let's again freeze 2 things, okay? So this is the shape of the sparsifier region, okay? So let me explain the shape. So first of all, these are how the Laplacians will look, okay? There are 3 parameters. There's A and C and B, A, B, and C, 3 parameters. So the picture is in 3-dimensional space, okay? So you can ignore this part. This is just the space of all these are all the Laplacians, okay? We can calculate it. But let's actually understand the space. So first of all, the space is curvy. So you see there's a quadratic inequality here, okay? So it's curvy, and that's what's creating this curve over here, okay? But everything else is linear inequalities. So I also need A greater than equal to 0, B greater than equal to, so I need this. Do you recognize this, what this is? The last 3. What? Yeah, so these are the 2 by 2 PSD matrices with A, B, B, C in it, right? If you think of the PSD condition, so this is, if you have 2 by 2 PSD matrices and you require this to be PSD, then the conditions are A non-negative, C non-negative. Did I change the order? Yeah, okay. Okay, so this is B, C, and C. Okay. So the bottom 3 conditions are coming from the PSD-ness of a 2 by 2 matrix, okay? That's the curvy piece. Okay, so what is this picture really, okay? So it looks like a boat, right? The top, there's a lid to this boat, and the lid is this A equal to 4 equation. That's the lid. So we want to be under that. So we can't see the lid, but there's a lid. And then there are 2 inequalities that look fairly symmetric, minus A plus root 2C less or equal to 4, minus A minus 2 root 2C less or equal to 4. They're the 2 sides, these 2 sides of the boat. Okay, those are the 2 inequalities there. And then there is one more, the back actually is not there, so it actually extends infinitely far. But when you draw it in Mathematica, they always put something in the back because they don't know how to draw it infinitely far. So in that direction, which I believe is the B direction, you can go infinitely far, okay? So the back of the boat is not there, but there is a lid. There are these 2 sides. And then there is this one inequality that touches the boat only in this point, okay? So it's like an inequality that touches this corner just like that, okay? And the rest of the boat is on the other side. So that's the only point of contact with the boat. Good? So these are all the inequalities that come from the calculation. We'll understand the calculation in a second. And this is the shape. Okay. So then what properties remain if you compare to the previous picture, which was just the orthin, right? It's definitely not polyhedral, right? There's some quadratic stuff in it. So definitely not polyhedral. Convex, what do you think? Seems still convex, right? Even if the back is not there, it goes infinitely far. Seems convex. Anything else? Maybe that's all. That's obvious.
Is that the origin?
No. You mean the origin is this, I think.
Yeah, that's what
Yeah. It doesn't always have to have the origin because some inequality could cut it off, but it'll have a part of the PSD coordinate. That's where the curvy part is going to come from. Okay, so this is the shape. Okay, so again, you can attach different types of sparsifiers to the different pieces of the boat. Okay, so those are the inequalities, and when one of those inequalities holds tight, you're going to lose an edge or more than one edge. That's what's going to happen. So let's do just one example. So remember the lid of the boat is A equal to 4. So if that's tight, if you're lying on the lid, then you're going to lose the edge 1, 2. Okay? So this point over here will lose the edge 1, 2 because it lies on the lid. But it doesn't lose, what else will it lose? It also loses 1, 2 it will lose, and then 3, 4 it will lose. Where is that coming from? A minus 2b. Oh yeah, it'll lose and one more edge because remember I told you there's an inequality that only touches the black point. When that holds an equality, you will lose 3, 4. Okay, so it loses these two edges, this point over here. So every single point in this yellow structure corresponds to a graph. That's a sparsifier of the original graph, and you can figure out its weights. Okay, so maybe it all looks very mysterious how this is all happening, right? So I want to actually try to explain now where this comes from.
Is there a reason why you chose this particular phi 2?
No. In fact, if you choose another phi 2, you'll get a slightly different picture. Okay? So because when you cut through fat eigenspaces, it depends on what you freeze, right? You'll get slightly different picture, slightly different sparsifiers too. Okay, so this we saw yesterday. There's semi-definite programming. We saw it. There's the PSD cone. There's a semi-definite program. Here it's written in a slightly different way from yesterday. So we are maximizing. So another way to think of a semi-definite program is you take the PSD cone, you cut it with some linear equations, affine equations in matrix space. So you cut the PSD cone, and then you maximize some linear function of the in matrix space. Okay, and these are spectrahedra. These are the feasible regions. We saw this yesterday. Okay, so I claim that this is the structure of the sparsifier set, and then we're going to prove this in a minute. Okay, so I claim that if you choose to freeze the first k eigenvalues and eigenvectors, then first of all we can put the first k eigenvectors into a matrix. This is called capital phi k. We can put all the rest into another matrix, which I'm going to call phi bigger than k. And then this is the diagonal matrix with the first k eigenvalues. Okay, so we are freezing this and we are freezing this. And we're not going to worry about this, but I'm just giving it a notation, okay? Then I claim that the space of sparsifiers, their Laplacians will look like, from the first k part, we will keep this. We'll have phi k, lambda k, phi k transpose. This part will stay. Then we'll keep another little thing that also is from the frozen part. So everything from here to here we have already. We've chosen to freeze. But then there is some variable part that involves the bigger eigenvectors and an unknown matrix Y, which has to be PSD, and then there are some conditions. Okay. All right, so this is where those pictures came from. So if once we understand why this works, then you can draw all the pictures. Good? So in the rest of the time, I'd just like to prove this theorem. I'd like to prove that this is exactly the structure of sparsifiers. Okay? Let me just see what else is here. Yeah.
So lambda k is associated to all the other.
You mean this lambda k?
No, small next term, second.
This one?
Yes.
Yeah, this is just the kth eigenvalue. And these are the bigger eigenvectors. So this part we are freezing and this part is unknown. Okay, so it does look very, very mysterious. So I'm just going to try to prove it. Okay? So let's shut this down and we're going to prove this theorem. Everybody okay? And then from this you see, if you draw this, you will see that, so the variable is y. Okay, y is a PSD matrix. But there are some linear inequalities and linear equations as well. That's where all those flat sides and all came from. Okay? So in the boat, this part is giving you the curvy part. This part is giving you all of those inequalities, the sides, the lid, all that. And then there are some equations, but equations only exist whenever there are non-edges in the original graph. So in K4, every edge was present, so there were no equations. Okay? All right, so that's maybe a good time to stop the talk, and we'll actually prove it. Okay, any questions on this before we do the math?
So the edges so which edges don't? The weights of the edges don't change?
They do. So you will see, because when y changes, this Laplacian keeps changing, and the Laplacian controls the weights, right? They do. So this is just guaranteeing that no new edges can appear. So the ST entry in the Laplacian, whatever we construct, has to remain 0 if ST was not an edge. So the bottom is to guarantee that no new edges appear. This one is to guarantee that whatever edges appear, they have to be in the Laplacian with a negative weight or a 0 weight, right? This is just making sure it looks like a Laplacian, and this is making sure no new edges appear. And then everything else is going to guarantee that this is actually isospectral, k-isospectral, it is a Laplacian, it comes from the graph, all that. Like, it has to do a lot of work, right? So it has a lot of stuff to achieve. Okay, so let's shut this down and prove the theorem. Okay. Okay, so let me put all the data that we have over here, okay? We have a big board, okay, so we can put it here. So I started with a graph that looked like this, E, and some weights. This is how we started. And its eigenpairs were 0 and phi 1, lambda 2, and phi 2, all the way up to some lambda k and phi k, all the way up to lambda n and phi n. This is of the Laplacian. Okay, so this is all coming from the Laplacian. Okay. The phis are orthonormal and all that, okay? So what we're doing is we are fixing these many. So fix these. Okay, so I want to calculate all the subgraphs where the first k eigenpairs are frozen and everything else can be whatever. Okay, that's what we want. Okay, so let's make a few definitions. So we're going to let capital phi k be all these, it's a matrix that contains the first k eigenvectors as columns. So this is an n by k matrix. And then we're going to let phi bigger than k be the rest. So this is phi k plus 1, up to phi n. So this is a n by n minus k matrix. Okay, these are both matrices. So we've just split the eigenbases into two parts. That's what we're doing here. Okay. All right, and then I'm also going to fix, let's let lambda k be the diagonal matrix that contains 0, lambda 2, all the way up to lambda k. Okay, this is the part that we want to freeze. So that's a k by k thing. And then the claim is that, so the claim is that the k isospectral subgraphs of G, this is the space of Laplacians. These are all matrices that look like phi k, lambda k, phi k transpose. Okay, so it'll have this piece, plus it'll have little lambda k, just the last eigenvector, times phi k transpose. So this much comes from the frozen part. So greater k, yeah, greater k. So this is the fixed part, so we'll call it f. And then it'll have another piece which is phi greater k times y times phi greater k transpose. And the conditions are that y is PSD. So y is actually a small matrix. It lies in Sn minus k plus. And then it has some linear conditions as well. So LST is less or equal to 0 for every ST and edge. And LST is equal to 0 for every ST that is not an edge. Okay? All right, so that's the claim. Sorry, the last part is a little confused, but that's the claim. Okay, so we'll come back and clean it up. Okay, everybody okay? That's what we're doing. Okay, so let's start to look at, so let's call the sparsifier G tilde. Call the K isospectral sparsifier, not the, call A sparsifier G tilde. Okay, so we're going to call this G tilde. These are the things we're looking for. We're actually going to collect all the Laplacians, but it's the same, right? We either find the graphs or we find the Laplacians, same information. Okay, so that's G tilde. Okay, so now, how does the Laplacian of the original graph look, right? So the original graph has a Laplacian that looks like, how does it look? So it has this, all the eigenvectors together. So let's say this is the part we froze. So this is phi k. This is phi bigger than k. And then it has all the eigenvalues, 0, lambda 2, up to lambda n. And then it has the transpose of that matrix. So this will look like phi k transpose, phi bigger than k transpose. Does everybody agree with this? This is the spectral decomposition of the Laplacian of the original graph. Yeah? Good? Okay. So I want to break this apart. I want to take the phi k part to one side and the rest to the other side. So do you remember that sometime before we discussed that this is the same thing as sum of lambda I, phi I transpose? This is the rank 1 decomposition. So that thing is the same thing as lambda I times, this is a matrix, so phi I is a matrix, and phi I transpose is a row matrix. So altogether this is a matrix. This is an n by n matrix. Okay? So this is the way to write the spectral decomposition as a sum of rank 1s. Good?
N.
Yeah, n to n, and 1 to n, correct. 1 to n. Okay, so this we know. So what we want to do in the new one, so if I want to construct Lg tilde, I want to preserve this much, right? I want to preserve this part. I want to preserve up to the kth piece, and I want to preserve this part. So these are the things I want to freeze. And I want to allow freedom in all the parts I didn't shade, okay? So that means from this expression, I can pull out the first k piece and freeze it and say, okay, I'm allowed freedom in the rest. Do you agree? So that's where the first piece comes from in this expression. So I'm going to freeze this much of the Laplacian. So this is the orange stuff, okay? So this much we freeze. So maybe I should put it in orange. So we're going to freeze the phi k, lambda k, phi k transpose. Okay, so that's all this orange stuff. That's this. Okay, and then after that we're allowed to do whatever we want. So after that we can have some other set of eigenvectors. I don't know what they are. Psi. Okay, and some other diagonal matrix. Let's call it D. And then I need to have psi transpose. Okay, so I don't know what they are. We have freedom to pick the psi and the D and all that. But I need to make sure that the first k piece is frozen. Do you agree? So what we're trying to do is we are trying to replace this phi k over here with the psi. So yeah, everybody sees what's happening. So we have freedom with this part, and we have freedom with this part, and we have freedom with this part. Okay?
To make sure that these are orthonormal to.
Correct. So now we start to have impose conditions. Okay? So the new Laplacian has to look like this, first of all, right? But now it also has conditions, as Arvind said. So what are the conditions we need? So such that, so let's make conditions. So this can't be just willy-nilly anything, right? So the size that we chose have to be mutually orthogonal, and they also have to be orthogonal to the phi's we froze, right? So those are two things that have to happen. So what we need is that if I look at the part we froze, this transpose, the psi, has to be 0, right? This means that all the phi vectors are orthogonal to all the psi vectors. Right? This is the part we froze. So these are column vectors. These are row vectors. So if I take the row vectors inside phi k transpose, then it must dot with all the psi vectors, which are column vectors, to give me 0. So all the psi's have to be orthogonal to the phi's that we froze. That's true. And it's also true the psi's themselves have to be mutually orthogonal, right? That's important too. So we also need that psi transpose psi is 0. Okay, so we need these two conditions. So if we have these two conditions, we do have an orthonormal set of, let's assume they are orthonormal. Identity, sorry, identity. It's a small identity, so we need n minus k. Right, so we need that to work out. But we need one more thing, right? This D thing, this D matrix is filled with some eigen, so let's say this D thing is it's a diagonal matrix. Let's call it mu k plus 1 all the way up to mu n, okay? Let's give that the name of the new eigenvalues that we are allowed to choose, right? But they have to be, see, they have to, what is the condition on this? Do you see? Just a little louder, I can't hear up here. Yeah, so you have to make sure that all of them are greater than lambda k, okay? Amongst themselves, they may be whatever order because we can reorder them, but all of them have to be greater than lambda k, right? Because we don't want to mess with the low part of the spectrum. You don't want these guys to creep into the low part, okay? In the Spielman-Tang model, they do creep. So they will scramble the spectrum. If you just try to preserve the quadratic form, you're not guaranteed that the first few eigenvalues are frozen, or even they are still the smallest k eigenvalues. They will all mess up, okay? Because they don't, it's not as strong as what we're trying to do. Okay, so the third condition we need is that all these mu j's have to be greater or equal to lambda k for all j. Everybody okay? So how they're ordered is not so important. Do you agree with that? Because you can just reorder them, and write them in correctly if you want to write it like that. But we have to make sure they're all greater equal to lambda k. Okay, that's it. Those are the conditions. Do you agree? Okay, so now let's actually, yeah?
This phi by transpose is going to be a full matrix, right? N by N matrix.
No. We only require n minus k extra eigenvectors, right?
No, but the whole thing is n by n.
Size.
Product it would be an N by N, right?
This? Yeah, as a product it will be n by n. Okay, right, correct.
Sum only, not
Yeah, that's right. So psi will look like this, and then it'll have a d, which is small, and then it'll have this psi transpose, which will look like this, right? So this is psi transpose, and this is d. But it's true that when you multiply psi with psi transpose, you'll get something n by n. True. Correct. Yeah. Okay, everybody okay so far? Okay, excellent. Okay, so now this is where you have to think what to do, right? So we need to construct these psis and these mu's and whatnot, okay? Mu's may be less important, but let's try to construct the psis. So what do we know about these psis, right? So first of all, a good candidate for the psis, if we're not very ambitious, is to just plug in the phi greater than k part, right? That's a candidate, that'll satisfy all these conditions, okay? So let me draw a picture. This is going to be very cartoony. So this is, let's suppose this is the span of the first k eigenvectors. Then I know that the last n minus k eigenvectors come from the complement, right? So this is the span of phi k plus 1 up to phi n. Do you agree? So if I take the span of the first k eigenvectors, then all the other eigenvectors are orthogonal to the first k. So I have all of space divides into span of phi 1 through phi k plus direct sum the span of the rest, right? So these two eigenspaces. So the phi k's are living here, okay? So the phi, okay, this is too small a picture. Let's enlarge that picture, okay? So this is the picture of, this is the span of phi k plus 1 up to phi n, okay? And the phi k's themselves are some orthogonal vectors that are living here. They're orthogonal, right? So the size, what do we know about the size, right? Where should they come from? These new things, we don't know what they are, these guys. They have to be orthogonal to all the previous phi 1 through phi k. And they have to be mutually orthogonal too. But do you see that they come from this vector space, right? Because they're orthogonal to phi 1 through phi k. This is the orthogonal complement of phi 1 through phi k. So this is the span of this, and this is the orthogonal complement of the span of, this is equal to the span of phi 1 through phi k complement, okay? So the size also have to come from this eigenspace. I mean, not eigenspace, subspace, okay? It has to come from this part of Rn, good? They have to be mutually orthogonal to each other too, right? These are orthogonal. These are phi k plus 1 up to phi n. These are there. They are orthogonal to each other. So it's like this, okay? They are like this. And the next set we have to find has to come from the same space, also orthogonal. So do you see how to relate them? So these are two orthogonal things living in the same space. Orthogonal, orthogonal. So you can just rotate this into this. Do you agree? There's an orthogonal transformation, not rotate necessarily, but there's an orthogonal transformation that takes you from here to into this. Okay? So the psi and the phi bigger than k are related by an orthogonal transformation. Do you agree? Yeah. All right. We are allowed to mess up eigenspaces, right? The psi's are not going to keep the other eigenspaces intact. So that's fine. So the key observation is that the size, this must also be the span of psi 1 through psi n minus k, right? They have to come from that space, They have to be mutually orthogonal. This will guarantee that they're orthogonal to the first k eigenvectors. So the key thing the key property is that psi is really, you take the eigenvectors that you did not freeze and then multiply it with an orthogonal matrix. So this is in O n minus k. Okay? So B is my orthogonal transformation that takes me from the given last n minus k eigenvectors into whatever psi is, it's a transformation. Do you agree? There's nothing else that can happen because this is orthogonal. I mean, what we want is orthogonal, what we have is orthogonal. They're living in the same eigenspace, they both span that space. So the only way to put this into this is to make an orthogonal transformation, okay? Which rotation, reflection, you're allowed those kinds of things. That's the only move that you can do. Exactly, it's a change of basis in that subspace, correct. Yeah, special change of basis, okay? So this is how psi will look. That's pretty cool, right? So we have a handle on psi because it's just an orthogonal transformation of what we dropped. What we didn't care about, this is an orthogonal transformation of that. Okay, that's the first observation. Okay, excellent. So now we're in business. So now we can plug in into this expression over here. Let's plug in what we just constructed, okay? So into this expression, so now I have L is equal to phi k lambda k. This is L of g tilde. Phi of k transpose, that is the orange piece. Okay, let's keep it orange. Okay, so we have, it's not the same orange. Okay, this is the Seattle orange. Okay, so it's not even that. Okay, phi k lambda k, phi k transpose, that's the frozen piece. Okay. Plus, now I'm going to plug in for psi. I know what psi is. So psi is phi bigger than k, b, times d, which we don't know, and then the transpose. So that's b transpose, phi bigger than k, transpose. Everybody okay? Is there a question here? No complaints? All good? Okay. Everybody good so far? Okay, so this is what we got, okay? All right, so that's great. And now we can just group this together. I'm going to call this matrix from here to here. Let's call it X, okay? So this is some matrix that I don't know, so this is X. Now I'm going to look at X. Let's look at X kind of deeply and see if it comes out nicely, okay? So what exactly is this X? So if I look at the space of X, okay, so this is going to now use some of the ideas we learned yesterday, okay? So let me erase some stuff. Yeah. Okay. So X looks like B, D, B transpose, where D is filled with eigenvalues. I mean, it's a diagonal matrix, but every diagonal entry is at least lambda k, right? So every lambda entry is positive, okay? So what we have is that the DII is strictly positive for all I. We have that, okay? B is orthogonal, D is strictly positive diagonal matrix, B transpose. What kind of matrix is that? I think someone's saying the answer. Diagonalizable, yes, sure, yes. But what kind of matrix? Positive semi-definite, but more, right? It's positive definite because its eigenvalues are exactly the diagonal entries of D, and they're all positive by construction. So this is exactly the set of positive definite matrices. I mean, this is positive definite, let's say that, okay? It is positive definite. Does every positive definite matrix look like this? Of this size. This has size n minus k by n minus k, right? So every positive definite matrix will look like this actually, right? It'll look like orthogonal times diagonal with all positive entries times, I mean, I'm not imposing this thing yet, okay? Let's not impose this yet. I'm just imposing that it's positive, okay? So if I just have this condition, let's just look at this condition. So the set of all x's such that this happens is exactly the positive definite matrices of size n minus k. Do you agree? I haven't yet imposed that all the diagonal entries have to be bigger than lambda k. I'm just saying if all the diagonals are positive and you look at BDB transpose, that's exactly the space of all positive definite matrices. Okay, so now let's impose this condition. Okay, so I don't want just any diagonal. I want to make sure that all of them are at least lambda k, right? So do you see how to write it from what we learned yesterday? So what we require is that the D thing, which is filled with these unknowns, so D11 up to Dn minus k and minus k.
We call that mu1.
Yeah, okay, we can call it that. Okay, so let's call it mu1 through mu n minus k. I want to make sure that all these guys are at least lambda k.
So we want B minus lambda k identity to be positive.
Exactly. So what we want is this matrix to be greater in the lower order than this matrix. Do you remember this trick? Oh, I'm sorry. Okay, let me not call them anything. So what we want is D to be greater equal to lambda k I n minus k. Do you agree with this? So if I want all the so this will guarantee for me that all the eigenvalues of D, which are the diagonal entries of D, are at least lambda k. This is what we need, right? This we saw yesterday. Okay, so this is what we need. So this is what happens to D, okay? So D needs to have this property. So, but what happens if we conjugate D? If D has this property and I multiply it on both sides with B and B transpose. So if I do B, D, B transpose, then does the eigenvalues change? No. So this is also greater equal to lambda k I n minus k. Okay, so you can check that if you, this is called conjugation, when you multiply with orthogonal and orthogonal transpose. If you do that to any matrix, the eigenvalues cannot change, okay? So this is also true. So I can conjugate and this is also true. Okay, very good. So then remember this is our x, right? The x is this, BD, this thing, okay? So this is x. So what we have is that x is greater in this lower order than this. So that's exactly the same thing as saying that if you subtract lambda k I n minus k from x, then you get something that is PSD. Do you agree? Why? Because we're saying that x is bigger than this in lower order. The meaning of that is if you take this minus this, you get something PSD, okay? So that x minus lambda k I n minus k, I'm calling it y, and whatever that is has to be PSD, okay? That's what it means to be greater. Any questions? Please ask. Did I lose you anywhere? We're almost done. Oh. Yeah, we're almost done with time too. 2 minutes. Okay, so we're done. This is where we are, okay? So now we're good, so we just plug it in here, okay? So if I plug it in here, I get the orange still, so let me not rewrite it. So I'm just going to erase this if you don't mind. This is the x, okay? So instead of the x, I'm going to write, what is x now? So x is going to be y, or rather lambda k I n minus k plus y. Okay, that is x, right? I just took it from there and stuck it there. Okay, now we're good. So now we just rewrite this. So this is phi k, lambda k, phi k transpose, plus I'm going to, this piece and this are also like part of the data that we are freezing. So I'm going to pull it out. So if I pull it out, lambda k is a scalar, it comes out. Identity doesn't do anything. So I have phi bigger than k transpose that came from all the orange pieces. And then I'm left with the part that I have freedom on is phi bigger than k, y, phi bigger than k transpose. Okay? So that's basically the structure of the Laplacian. But then you also have to impose that whatever this matrix is, this L, you want to make sure that you don't suddenly collect some extra edges, right? Edges that didn't used to be there should still be 0. So if I look at, so we also need that, so let's write it here. We also need that if you have an edge, if LST must be 0 every time ST was not an edge before. So I want to keep the 0, 0 in the Laplacian. And I want to make sure that in the edge positions, I get something less or equal to 0, right? In the Laplacian, all the weights are negative on an edge. So this must be true for every ST that is an edge. So we need these two conditions as well. Because you can have PSD matrices. Okay, we have to verify some things. We have to verify that this construction gives us something PSD. We have to verify that it is a Laplacian. And we have to, these conditions will ensure that it's a sparsifier. Got it? So there's a little piece left to verify that that construction gives us something that is truly PSD and has the right, just PSD. PSD is all we need. Weakly, all the conditions of a Laplacian you should check. So that's kind of a mechanical check. You can check that it'll work out. And we do need these conditions, okay? So, and we need that Y is PSD. So we also need this condition. This condition. So that's all the pieces of the theorem. So it's saying that the Laplacians look like, freeze the first k piece, then freeze a little bit more, okay, to guarantee that all the eigenvalues that are coming later, at least lambda k, freedom here, but this piece is fixed. So only y is moving, y is PSD, and these linear equations and inequalities. Okay, so in the next session, we'll actually compute one of these. We're going to compute the butterfly graph using this calculation. Good? That's the easiest. The complete graph is a little hard. You can do it at home.